Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on December 8th, 2025, about 3 days ago. It shows that reinforcement learning can genuinely extend a model's reasoning abilities, but only when training targets problems right at the model's edge of competence, delivering gains up to 42% in pass at 128 on harder reasoning tasks. The paper is titled, On the Interplay of Pre-Training, Mid-Training, and RL on Reasoning Language Models. And as we will see later, the implications for how we stage model training are quite significant. Alright, Figure 1 pulls the main story together by comparing how different training stages shape reasoning performance. The left panel shows that reinforcement learning only gives big gains when it trains on tasks just beyond the pre-training range, not on too easy or impossibly hard ones. The middle panel illustrates that even about 1% pre-training exposure to rare contexts enables strong transfer. The right panel demonstrates that inserting a supervised mid-training phase before reinforcement learning yields much better performance at high task difficulty under the same compute budget. Well, Figure 2 explains how the authors set up this controlled playground for reasoning. Panel A shows the data generation framework, where a dependency graph and a contextual template such as a zoo story are rendered into a full math word problem and solution trace. Panel B describes the task setup, separating extrapolative generalization over difficulty from contextual generalization across templates. Panel C details process-verified evaluation, where a parser reconstructs the predicted graph and only rewards answers when every intermediate step and the final result match the gold graph. So while Figure 2 described the setup, Figure 3 shows how reinforcement learning behaves across easy, medium, and hard problem ranges. The left panel reveals that for in-distribution tasks, reinforcement learning mostly boosts pass at 1, but leaves pass at 128 unchanged, so no new capability appears. The middle panel shows large gains when reinforcement learning trains on edge of competence problems, just beyond pre-training. The right panel indicates that when tasks are much harder, only the policy trained on those edge problems generalizes upward, whereas training directly on very hard data barely helps. Alright, Figure 4 drills into how much pre-training exposure a model needs before reinforcement learning can transfer to a new context. The overall figure plots pass at 128 on context B as task difficulty, measured by solution steps, increases. The first two panels show that with 0 or only 0.1% context B in pre-training, reinforcement learning fails to generalize. The last two panels show that once exposure reaches about 1% or more, reinforcement learning suddenly enables strong generalization, even on the hardest problems. So while Figure 4 focused on contextual exposure, Figure 6 compares how different mixes of mid-training and reinforcement learning affect performance under a fixed compute budget. The left two panels show pass at 1, where full mid-training or light reinforcement learning give the best accuracy on edge of distribution tasks, while heavy reinforcement learning helps only slightly. The right two panels show pass at 128, where heavy reinforcement learning clearly boosts out of distribution hard problems, but only when some mid-training still provides the underlying reasoning priors. Okay, after those aggregate curves on training strategies, this example instance shows what a single synthesized problem actually looks like. The top orange box presents the question in natural language, which wraps a fairly complex dependency graph into a story about schools in different cities. The large green box contains the step-by-step solution, where each variable and intermediate equation gets spelled out explicitly. The bottom purple strip gives the final numeric answer, which the evaluation only counts as correct when every solution step is also structurally valid. So, after that concrete problem example, Figure 15 quantifies how pre-training difficulty shapes what reinforcement learning can add. The left panel shows that on easy tasks, increasing hard problem exposure mainly boosts the base model, so reinforcement learning gives almost no extra gain. The center panel shows that for edge of competence tasks, moderate hard exposure around 20% lets reinforcement learning add roughly 20 to 40 pass at 128 points. The right panel shows that on the hardest tasks, more hard pre-training steadily raises the reinforcement learning curve, while the base model stays near 0, so reinforcement learning delivers the entire capability lift. So the big message is that reinforcement learning does extend reasoning, but only when 3 ingredients line up: seed skills from pre-training, a supervised mid-training bridge, and reinforcement data right at the model's edge of competence. That recipe also reduces reward hacking and improves step-by-step fidelity. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.